All right, so we'll pick it up with number 5. There's Katie. She's probably on the road. I'm gonna let her sign in if she's gonna be here. All right. Number 5. Barium carbonate has a measured solubility of 4.03 times 10 to the minus 5 at 25 degrees C. If we don't tell you what the solubility are in molarity, right? So when it says 4.03 times 10 to the minus, that's molarity. So that would be using our convention, that would be S equals 4.03. I'll mute her. So the question is determine the KSP. All right. So the first thing we have to do is write the balanced equation for the solubility of barium carbonate. So this is where you got to go back to first semester and remember how to write the compound. Barium and carbonate, which is a polyatomic ion. That's a 2- charge, and barium is a 2+ charge. Okay? So that's all you need right there. 1 barium and 1 carbonate. This is a solid. And it's going to be in equilibrium with barium ion and the carbonate. Okay. Now for clarity, this first one, I'm going to do the whole ice thing. Okay. We have, let's see, we start off with, of course, 0 here, 0 here. But when this goes into solution, we get this much of that in solution. And since the ratio is 1 to 1, we have both of these. And then, of course, there's no other change. So at equilibrium, we have this concentration in molarity of those 2 ions. Now we can write the equilibrium expression. The KSP is our unknown. That's what we're asked to find. And we're going to have barium ion concentration, carbonate ion concentration, and to the first power. So all we have to do is, right, if both of these are going to be equal, I'm just going to say 4.03. Am I using the right number? Mm-hmm. Yeah, okay. Times 10 to the minus 5. And this is squared. So the KSP is just going to be that value squared. And significant figures, 1.62 times 10 to the minus 9. That should be the KSP. Okay. All right. All right, next one. Number 6. So this one's going to be in terms of 10,2 hydroxide. So when 10,2 hydroxide goes into solution, right, it's in equilibrium with 1 of these ions and 2 of these ions. Okay. So the correct mathematical expression for finding the molar solubility of this one is, all right, I'm going to do the whole ice thing for this one too, just for clarity. we start off with 0. And then when we lose one of these, we get one of those. Because the coefficient is 1 to 1. Right? And for this one, we get 2 of them. Right? For every one of these that goes into solution, you get 2 hydroxyls. So we have S and 2S there. And the expression for KSP is going to be, let's be complete. We can take shortcuts later. And that's squared. So that means we're going to put S here and 2S here squared. Okay. So if we reduce that mathematically, we find this is 4S squared times S is 4S cubed.
No. Repeat that, sorry.
Okay. I squared everything inside here. 4S squared, and then times S adds another S. So instead of S squared, it's S cubed.
Okay. I get what you did.
Okay. And that would be D. Now, if you work enough of these, you can work that out in your head. All you need is the balanced equation to show you what terms go into the KSP expression. But I'm doing this complete now because y'all are in kindergarten.
We are.
Okay, number 11. Which of the following compounds has the lowest solubility in molarity? All right, let's I think we need Henry Ford for this one. Is that many? Yep. Okay, so the first one is silver phosphate. Second one is one we just got through with. And then we have CDS. And we have calcium sulfate. And aluminum hydroxide. Notice one thing about these comparisons. These are going to produce different numbers of ions, each one. Well, some of them are the same, but they're not consistent. You don't have the same number of ions produced when they go into solution. If you do have a comparison where you say, let's say we have all of them have one cation, one anion in the compound. In that case, you can compare directly the KSPs to determine solubility because the expression for solubility is going to be exactly the same for each one. But when you have differences there, you have to actually determine what is the solubility. All right, so we've got 3 silvers, and I'm going to save some space and leave out the aqueous part. And then here, we did this one before. There we go. This one is 1 cadmium, 2 plus, and sulfur, 2 minus. Calcium is a 2 plus, sulfate, 2 minus, and aluminum is a 3 plus. Then we've got 3 hydroxyls. So there's your expression. And if we assign solubilities to each one of these, we say we're going to lose a certain concentration here of each one of these, then how many does that produce on this side? Right? And based upon this expression, KSP equals these two, the cation and the anion, to some power. Right? Then we can set up, let's see, our let's do KSP. KSP. I'm trying to streamline this thing. For the first one is 1.8 times 10 to the minus 18. The second one is 3 times 10 to the minus 27, and then minus 28. And then 6.1 times 10 to the minus 5, and 2 times 10 to the minus 33. Okay. So we know that this one is going to be, for every one of these, you get 3 of those. Right? So this would be 3s, and this would be 1s. Right? And this would be cubed. Right? So it's 3s cubed. Like that, times s would be the expression for that one. Okay. And this one, of course, we did this one earlier. This one has s for the cation, and then 2s for the anion squared. And this one is 1 to 1. So this is simply just s times s. And this one is 1 to 1. So it's s. S. Okay. If we were just comparing these two right here, this is more soluble than that one because they use the same expression. But the water's muddy, so we have to do them all separately. This one is an S for aluminum. Right, 1 aluminum to the first power, and then 3s for the hydroxyl to the third power. Okay. All right. So let's reduce this. That's 3 times 3 times 3 is 27, right? So it's 27. S cubed times s is s to the 4th. And this one, we did this one earlier. This would be 4s cubed. This would be s squared. This would be s squared. And this would be same as that one. 27s to the 4th power. Okay. All right. So now what we have to do is solve for s for each one. I'm going to put those values over here. Survived.
But yes,
I was
made it
told.
out alive.
Okay, so what we need to do here is divide that by 27. Right? Divide this one by 27, then take the 4th root of it. Okay, very good with that math.
Divide by 27 and then just
Take the 4th root.
take the 4th, like,
Yeah,
to the
like,
4th power. The
Right.
answer to the 4th power, right? Is that what you mean?
no, 4th root. If you want to use powers like I have to do in my calculator, it would be to the 1/4 power. But if you have a root key in your calculator, you would do the 4th root. All right. So if I take 1.8, exponent minus 18, and then I divide by 27, and then I take my 4th root of this, that. I get 1.6 times 10 to the minus 5. 1.6 times 10 to the minus 5. And this is molarity. This is solubility in molarity. Okay. So this one, we divide that number, 3 exponent 27. Okay. Divided by 4. Right. And then take the 3rd root. Okay. So on my calculator, it's 0.3333 to the power. And I get 9.1 times 10 to the minus 10 molar. And this one, you just take the square root. Square root of both sides. 8. And there's my square root. There's my square root. 1 times 10 to the minus 14. I should have been able to do that one. Good. Okay. And same thing for the next one. Just take the square root of 6.1 to the minus 5th power. And do that again. Why does it give me standard notation? I didn't tell it to do that. Oops. Hold on a second. I'm going to correct my display. 6.1 times 10 to the minus 5, and I take the square root. There we go. 7.8 times 10 to the minus 3. Now you guys get the same numbers.
Yes, so far.
Okay. And the last one is like this one, right? Divide this by 27 and take the 4th root out of it. 2 exponent 33, 27, and then take the 4th root.
Sorry.
What'd you get?
I messed up. Hold on.
Okay.
Okay. It's right. Repeat that other one, what you just said.
This last one?
Yeah.
Okay, right. This is equal to that. So we divide both sides by 27. Divide that by 27. Uh-huh. Okay, do you got a number?
Divided by 27.
Uh-huh.
7.40.
Okay. Then you take the 4th root, or the 1/4 power, whichever your calculator has. If you've got a root key in your calculator, you can just put in 4.
Yes, yeah, so. It might be easier to write this number down and instead of.
Not working.
There's one more, yeah, put it all. Maybe then have the minutes, not really. You know how to work this way?
Algebraic calculators and I don't get along. That's why I use RPM.
See, you could put this one because it's getting the stuff on the floor, so it's trying to get over. It's not like
May have to go back to the user's manual. Okay, here's what I got.
I got 2.9. So then, well, not 10 to the right.
Yep, -9.
Yeah.
Okay, now we can compare the solubilities, right? What's the question? Lowest solubility. Right? So, to save time, I look at the powers of 10. Right, they're all different. So all I have to do is say which one has the smallest power of 10. It's this one right here. 10 to the minus 14 is the smallest. Right. So cadmium sulfide is the least soluble of those compounds. All right. That's how Henry Ford would do it. Well, except he charge you for it. I guess I'm charging you for it too, man,
Yeah.
indirectly. If you get the pinch and you already know how to do powers in your calculator,
I'm trying to Google it, but I was.
okay. If you know how to do powers like x to the fourth power or something like that, then instead of trying to use the root key, just use the powers that you know how to do and do the power to the fractional of the 4, 1/4 power, 0.25. And that should work also. At least that's the way I have to do it on my calculator. All right. Let's see, 13. The molar solubility of barium carbonate is 1.6 times 10 to the minus 9 in 0.1 molar barium chloride solution. Oh, the molar solubility in 0.1 molar barium chloride solution is what? So we're looking for the solubility, but now we have a common ion in solution already. That's going to affect the solubility. Now, will it affect the solubility constant? No, the KSP will be the same. All right, so we've got barium carbonate again. And we're going to put it in solution. Carbonate. All right, so we have our ice table. And we're starting out with no carbonate, but we do have 0.1 molar barium. Oops. Barium. Oh, we put it in there as barium chloride, which means if we have 0.1 molar barium chloride, chloride is not common to this, right? It's a spectator. So we're focused on the barium. 0.1 molar barium chloride is 0.1 molar barium. Right, so those are starting conditions. And then we lose some of that and we gain one of those over here. How do we know it's going that direction though? Like Le Chatelier. There's no carbonate over here, right? It has to go that way. So we know it's going this way. We just don't know the magnitude yet. All right, so for every carbonate, for every barium carbonate, we get one barium and one carbonate. So at equilibrium, we have 0.1 molar plus S and then S. Now we can write our expression, and 1.6 times 10 to the minus 9 is the KSP, and that's equal to that value, 0.1 plus S times S, right? And they're both to the first power. So what do we get here? We get, well, let me see. How big is S going to be compared to 0.1 molar? It's not going to be very big. I mean, even in pure water, this solubility is extremely low. And it's going to be even lower now. So I think what we do is say 0.1 is approximately 0.1 times S squared. Oops. Times S. Because we got rid of that S. Right? When we approximated, we said that S is not big enough to influence that value. So I said 0.1 over here times S. So S is going to be equal to that divided by 0.1. Divided by 0.1. So what does that give us? Well, that's 10 to the minus 1. Right? You divide by 10 to the minus 1. That means you subtract a minus 1 from minus 9, 1.6 times 10 minus 8 molar. Right? And none of these. Now, if I went the wrong direction with this, you might pick A. But it's not 10 to the minus 10. We're dividing by 0.1. 10 to the minus 1. So minus 9 minus a minus 1 is minus 8. Okay. So none of these. The answer is not there. All right. Let's see about 17. All right. Which of the following solid salts is more soluble in 1 molar acid than in pure water? Right. So we're comparing water solubility versus 1 molar hydrogen ions. Now, we're not told what the anion is. We're just told that it's this acid. And we have to assume that we're not using an acid that will cause any further precipitation. So, what are our choices? We have sodium chloride. We have calcium carbonate. We have potassium chloride. We have silver chloride and potassium nitrate. All right. This is really kind of dumb. Sodium chloride is completely soluble anyway. But what do we need to increase solubility by adding an acid? We need the conjugate base of the acid to be a strong base. This would be the conjugate base. And so if it combined with these two, it would produce hydrochloric acid, right? But HCl is a strong acid. It's completely soluble. This is a weak base. So the solubility is not going to change at all. How about this one? Carbonate. Is carbonate a strong base? It's very strong. If you get carbonic acid in solution, and I'm going to go through both. I'm going to put the overall equation: 2 hydrogens plus carbonate. We know it takes place in 2 steps. You lose 1 proton and get hydrogen carbonate, and then you lose another proton and get the carbonate ion. This is extremely strong base. That concentration, that solubility will be significantly affected by hydrogen ions. Why? Because when you add hydrogen ions, what do you get? H2CO3. If that's a strong base, it's going to pick up those hydrogen ions, produce this compound, and shift the equilibrium that way, making the calcium carbonate more soluble. Same argument here and here, and actually here, because nitric acid is a strong acid. That means this is a weak base, weak base, weak base, weak base. This is the only one that is composed of a cation with a strong base. That's why the increased hydrogen ion concentration will only affect this concentration, this solubility. Okay. All right. 19. And you have a solution consisting of 0.1 molar chloride and 0.1 molar chromate. Let's see, we're given 0.1 molar chloride and 0.1 molar chromate. Right? Too much. Okay, and you add 0.1 molar silver nitrate dropwise to the solution. So we're going to titrate this solution. Now we're going to add 0.1 molar silver nitrate. Right, so that's what we're actually adding. Nitrate is spectator. So we're adding this to dropwise. Okay, if you're given the KSP for silver chromate, silver, oops, let's try that again. Okay. Third time's a charm. Chromate, that's a 2. And that produces 2 silvers and a chromate. And then this one is referencing this reaction, solubility of silver chloride. And then let's see. Stuck in a rut. There we go. There. And the KSP for chromate is 9 times 10 to the minus 12. And the KSP for silver chloride is
1.6 times 10 to the.
yeah, thank you. 1.6 times 10 to the minus 10. Okay. Now I think we've got everything up there we need. Which of the following will precipitate first? All right. I think what we need to do is compare their solubility, their molar solubility. Oh, no, we don't. We need to do the Q value. Yeah, compare the Qs. All right, so Q for silver chloride would be equal to the silver ion concentration 0.1 times 0.1. Right. So that's 1 times 10 to the minus 2, correct? That's the Q. The Q for silver chromate is equal to silver concentration, right? We've got the same values, but we have a different expression because the silver is squared. Right? And the chromate is still 0.1. All right, so this is, let's see, square 0.1 is, well, 0.1 cubed, right?
Why are you keeping it?
Yeah, we cubed. Okay, I thought that's what it was. 1 times 10 to the minus 3. Okay, those are the Qs. Now compare the Qs to the solubility product. Right? For silver chloride, 1 times 10 to the minus 2 is greater than 1.6 times 10 to the minus 10. And 10 to the minus 3 is also greater than 9 times 10 to the minus 12. But how much bigger? Right? This is, well, that's almost 10 to the minus 11. So 3 from 11 is 8. So that's 8 orders of magnitude. And this is, that's 8 orders. It's not quite. It's a little bit. This is a little bit less than 8 orders of magnitude, and this is a little bit greater than 8 orders of magnitude. See what I'm doing? I'm saying this is 8 orders of magnitude difference, 10 -2 to -10. But this one, I rounded this one up to 10 to the -11, but it's not, it's a little bit less than 10 to the -11. So that's why I say it's, if it's 11 -3, then it's 8, but it's a little bit less, and this is a little bit greater. So what do we say about Q's? Right? If the Q is greater than the KSP, you're going to get precipitation. But we want to say which one precipitates first. The one that's the largest order of magnitude over the over its KSP. Right? This one is more than 8 orders of magnitude greater, and this one's less than 8 orders of magnitude. So this one should precipitate first, silver chloride. Right? Okay, now let me see how I worked it in the workout problems. I think I did it different in the work problems. I'm pretty sure I did. Let's see. Yeah, I compared solubilities. Right. So if you go through the process of comparing solubilities, what's the solubility of each one? It turns out that silver chloride is 1.3 times 10 to the -5 molar solubility, and silver chromate is 10 to the -4 solubility. So the one that's the least soluble would precipitate first. That's another way of approaching it. I just thought of this one off the top of my head. I'd never done it that way before. If you want to compare solubilities, then that's your way. You get the same answer. All right. And 21. How many moles of calcium nitrate must be added to 1 liter of 0.182 molar potassium fluoride solution to begin precipitation of calcium? Okay, here we are going to calculate the Q. All right, so we've got, let's see, we're going to add potassium fluoride to a solution of calcium nitrate to precipitate calcium fluoride. So the operating equation here is calcium fluoride, and that should be 2. And 2 fluoride. Right? Okay. We want to begin precipitation. So in order to begin precipitation, we start at where the Q is equal to the KSP. Right. So at what concentration would the Q equal KSP? KSP for calcium fluoride is 4 times 10 to the -11. 4 times 10 to the -11, and that's equal to concentration of calcium times concentration of fluoride squared. Okay. So we have 1 liter of solution. We have to assume that we're not changing the volume significantly when we add them together. Otherwise, the concentration is changing at the same time, and we've got a calculus problem. So if we've got 1 liter of solution and let's see, we start off with 0.182 molar fluoride. We got 0.182 molar fluoride. That's where we're starting, right? Okay. That's going to be squared. This is going to be unknown. Okay, we know this concentration already. That's what's in solution of the fluoride. So what we want to know is what's the concentration of calcium when this is equal. This would be like a Q calculation. And if this is equal to that, then that's when precipitation starts. This is the minimum concentration of calcium ions that you need. So if we solve for that one, we just need to square that 0.182. Okay, and then divide it into this value. And I get calcium concentration when precipitation starts is 1.2 times 10 to the minus 9th molar. Okay. That's the molar concentration of calcium. So how many moles of calcium nitrate? Well, calcium nitrate, right, is completely soluble, and it produces for every 1 mole of calcium nitrate, you get a mole of calcium. So this would be the concentration of calcium nitrate, right? 1.2 times 10 to the minus 9 molar. And since we have 1 liter of solution, how do we find the moles? Molarity times volume equals moles. Remember that? So if we multiply times 1 liter, we're going to get that many moles. So that's why the answer is 1.2 times 10 to the minus 9 moles. Okay. All right. It's 21. And 23 coming up. Okay. A solution of 0.01 molar in each of these: lead, manganese, and zinc. Solid sodium hydroxide is added until the pH of the solution is 8.5. Which of the following statements is true? All right. So the solubilities we're dealing here are the hydroxides of each of those metal ions. So we've got lead hydroxide, which is a solid, is in equilibrium with the lead 2+ ion and 2 hydroxyl. Okay, and I'm going to separate it a good bit. The next one we got, oh, and the KSP is 1.4 times 10 to the minus 20. KSP 1.4 times 10 to the minus 20. And then the next one in the list is manganese hydroxide, MnOH2, is in equilibrium with the manganese 2+ ion plus 2 hydroxyls. And its KSP is 10 to the minus 13. Okay. And then the last one is zinc. We have zinc hydroxide. And that's in equilibrium with these ions. And its KSP is 2.1 times 10 to the minus 16. And 16. Okay. That's given, and we're going to add each solution is 0.1 molar in each of these ions. 0.1 molar. Right? Because these are added as nitrate. And then we're going to add hydroxide by adjusting the pH to 8.5. Right? So there's going to be an excess of hydroxide ions. Right? 8.5 is basic. So you're going to have some extra hydroxides in there. What is the hydroxide ion concentration? Well, if pH is equal to 8.5, what's POH? That's 14 minus that, right? See, that'd be 5.5. Right? Now, what's the hydroxide ion concentration? Because that's what we're after. We want to calculate the Q for each one of these. Right? So the hydroxide ion concentration is equal to 10 to the minus 5.5. Change that sign. No powers here. This is, I'm going to put it down here. 3.16 times 10 to the minus 6 molar. So that's the concentration we have here. 3.16 times 10 to the minus 6 molar. 6, 10 to the minus 6. And 3.16 times 10 to the minus 6. So if we calculate the Q, and each one of these has the same expression for the KSP. Right? It's going to be this times that squared is going to give you the Q for each one. Okay? So what's the Q for this one? Well, let's see. I'm going to square this one first, right? Because that right there, this is squared. Oops. 3.16. Sign. And that's actually, we're going to have the same value for each one, aren't we? It just dawned on me. Right? You got the same calculation. This is squared, that's squared, that's squared. This is to the first power. So if we calculate one, we got the Q for all of them. All right, so let's see. I'm going to square that value right there. And I get 9.96 times 10 to the minus 12 times 0.1. And that's 9.99 times 10 to the minus 13. Okay. Compare this Q to each one. If the Q is greater than the KSP, we'll get precipitation. Right? So is the Q greater than that one? Yeah. 10 to the minus 13. This one precipitates. How about this one? 9 times 10 to the minus 13 compared to 2. This one precipitates. Right? It's just barely big enough. This one, 10 to the minus 13, is less than that one. This is no precipitation. So the only two that precipitate are the lead and the manganese, which would be, oh, excuse me. What did I do wrong? It says zinc and lead precipitate. Oh, okay. I'm sorry. My logic is messed up. This one's greater than that one. This one is greater than that one. It will precipitate. But this one should be less than that. Did I calculate that wrong? 2 times 10 minus 13. 19 minus 16. Okay. These two definitely. I did something wrong there. Let me be sure I got that calculation correct. 3.16 exponent 6 here. And square it times 0.1 is 9.99 times 10 to the minus 13. Or it's about 1 times 10 to the minus 12. Right? 1 times 10. Round it off. So that one's greater than this. So why is that? But I got to see what I did wrong. Let's see, is Q less than KSP? No, no. Okay, that's the right value. That's the right value. You got those values correct. Then we put 5.5. 3.16, 10 to the minus 6. Okay, yeah. Square that. 9.9, 10 to the minus 14. Okay. That's where I went wrong. Let me do it one more time. You guys didn't catch me either. Okay. Then times 1 exponent minus. Why do I keep getting minus 13? Oh, 0.01. Yeah. You guys let me get away with this. You just wanted to see if I'd catch it. There. So 0.01 times this is 14. There we go. All right, now we can compare. This Q is definitely greater than that one, so it precipitates. This Q is greater than that one, so it precipitates. This Q is less than that one, so it won't precipitate. It's a math error. That's what happens when I try to teach in a hot room. My brain overheats. All right, let's see, 24. In the qualitative analysis scheme for metal ions, how are the analytical group 2 cations separated from the cations of analytical group 3 and 5? Okay, go to the end. You're going to have this on the exam. It'll be your, how do we separate 2 from 3 through 5? All right, so let's go down and look at our separation tree. There it is. How do we separate 2 from the rest of them? All right, so we're at this point where we branch off 2 right here. Branching off that 2. We do it by adding hydrogen sulfide under acidic conditions. Right? It's already been acidified. Now we're going to add hydrogen sulfide, and that will remove group 2 from group 3 through 5. Okay, now we go back to the top. Well, not to the top, to 24. Here we go. So by adding hydrogen sulfide in acidic solution, we form insoluble metal sulfides. That's C. Okay. And let's see, let's go to 25. Which of the following solid salts should be more soluble in 1 molar ammonia than in water? All right. For this problem, this is the other way that you solubilize a sparingly soluble salt. Instead of attacking the anion, which has to be a strong base to use an acid. If we don't have a strong base, then we attack the cation by forming a complex ion with ammonia. And if we look at each one of those, right, A through E, what is the cation involved? In the first one, it's sodium. In the second one, it's potassium. In the third one, it's silver. Fourth one is potassium again, and none of these. So which one of these will form a complex ion with ammonia? The alkali metals will not form complex ions. They don't need to, because they're all soluble anyway. Right? Any sodium salt, any potassium salt, any potassium salt, any of those salts are completely soluble. They don't need ammonia. It won't change their solubility at the least little bit. This is your answer. Silver will form a complex ion with ammonia and solubilize silver bromide. I think today we're going to look at formation constant of silver, diamino silver. But we're using the solubility of silver chloride because we're titrating it with potassium chloride. If we wanted to do this one, silver bromide, we'd have to use potassium bromide instead. All right, 27. This looks like a repeat. Then we can do this one without the ice table. What's the mathematical expression for the molar solubility of lead 2 chloride? Lead 2 chloride. Right? 2 plus, 1 minus. All right, so that's going to produce what? It's going to produce this one plus 2 of these. Right? So if you look at the solubility in terms of S and S, this is going to produce 1 S for each one of these. This is going to produce 2 S's for each one of those. Okay? When we put it in the expression, this is to the first power, and this is to the second power. So 4S cubed would be equal to the KSP. Right? So D is your answer. That looks familiar. Okay. Let's see, what's the next one? Next one coming up. 30. Which of the following leads to the formation of precipitate? Oh, this is just memory. When your Q of known concentrations is greater than the KSP for the salt in question, you get precipitation. So C is the answer. $34. Calculate the solubility of silver chromate with a KSP of 9 times 10 minus 12 in 0.049 silver nitrate. We did one similar to this earlier. The solubility equation is this, right? And whatever goes in solution is in this stoichiometry. Okay. So what are we starting off with? Initial concentration. Well, we're 0.049 molar silver, because silver nitrate is completely soluble and it's a 1-to-1, right? If you've got 0.049 molar silver nitrate, you have 0.049 silver. So we're starting off with 0.049. Let me be sure I wrote that correctly. Yes. Right. So we're going to end up with, at equilibrium, right, we're going to lose something over here. And we're going to gain it here. Actually, 2 of those. For every one of these, we get 2 of these. Plus 1 of those. So our expression is 0.049 plus 2S over S. Right, so our KSP is 9 times 10 to the minus 12. 9 times 10 to the minus 12 is equal to what? Well, it's this value squared. Times this value. Okay. So if we don't want to have to solve a quadratic, we do a little mental gymnastics. And we say, all right, the solubility of this compound is going to be even less with this common ion already there. So that value right there is going to be very, very small, even relative to this one. So it's approximately equal to 0.049 squared times S. Okay, so I'm going to square 0.049, and then I'm going to divide it into that value right there. And I get S equals 3.7 times 10 to the minus 9 molar. Okay. Now, if we wanted to check the 5% rule, what would we do? We take this value, put it right there, put it right there, and calculate what that would be. Let's do that. Let's put that value in here times 2. Let's see, 2 times, and then add 0.049, and then square it, and then times 3, 6. So that gives us a calculated KSP of 8.9 times 10 to the minus 12. Okay, is that within 5%? Well, what's the difference between the two? 0.1, 0.1 divided by 9 times 100. That's 1%. So we were justified in doing that. Now, why did I leave? I left off the powers of 10 because it's the same for all of them. That just cancel out. So I only had to deal with the coefficients. Okay, I was just curious. I mean, we just assumed that it was correct, but that verifies that we're less than 5% off. If we wanted to get even closer, you know how to do that. Successive approximations. Right. Just plug that value into the S that we let go the first time and solve for the other S. And that'll get you even closer. Okay. 34, 36, and 37. All right. Let's see. It's a little after 10. Okay, we're good. How many moles of calcium fluoride will dissolve in 3 liters of 0.089 molar sodium fluoride solution? All right. Okay. We've done one like this before. The question is not the concentration, but the total number of moles. So we got to do an extra step. We're looking at the solubility of calcium fluoride. All right, so that's going to produce this ion and 2 of these. Okay. And the KSP is given as 4 times 10 to the minus 11. Okay. All right. Initially, we're starting off at what? Well, we've got fluoride in solution, 0.089 molar sodium fluoride, which is how much fluoride? 0.089, right? 1 fluoride for every sodium fluoride. So 0.089 molar is where we're starting here, and that's 0. All right, so if we lose one of these, how many of these do we get? We get 1 of those, and we get 2 of these. Right? So at equilibrium, we have 2S plus 0.09. Now we can say this. S for the calcium and 2S plus 0.089 squared for the fluoride. And again, that S is going to be extremely small. So we should be able to approximate by doing this. Like that. So if I square that, divide it into this, that'll give me my answer. And for okay, I get 5.0. S equals 5.0 times 10 to the minus 9 molar concentration of calcium. How many moles of calcium fluoride will dissolve? How many moles will dissolve in 3 liters? This is molarity. This is per 1 liter. So if we multiply molarity times volume, we get number of moles, right? Times volume, which is 3 liters. So I just need to multiply 3 times that. 1.5 times 10 to the minus 8. 1.5 times 10 to the minus 8 moles of calcium fluoride. Right? Yeah, see. That's the trick. It's the last step. We're not looking for solubility. We're looking for total number of moles in a given volume. All right. 37. What's the best way to ensure complete precipitation of SNS from a saturated H2S solution? Okay. We want to be sure that we precipitate all of this. And it's 2 plus and sulfur 2 minus. Okay. We want to precipitate all of this. Which way does that need to shift? This way. So you need a massive amount, excess amount of sulfur, sulfide ion. How do you get a massive amount of sulfide ion from a solution of H2S? Right? This is an aqueous solution, but what we don't need that, we need this. So we do this in aqueous solution and this in aqueous solution. So how do you get a massive amount of that? You remove the hydrogens. Right? How do you remove the hydrogens? The best way is to add a strong base like hydroxide. Right? Then you combine those two and it makes water. And that shifts the equilibrium this way, making huge amounts of sulfide. So if you add a base and increase the pH, the best way is add a strong base. And for inorganic chemistry, hydroxyl is the choice, the base of choice, the base of champions. Which was that breakfast food? The breakfast food of champions. That was Wheaties, wasn't it? Yeah, Wheaties. This is the hydroxyl. This is the base of champions, and that will ensure massive amounts of this one that will drive this reaction. These are two coupled reactions. We're coupling this one to that one, and we're modifying this one so that we can excess this. All right. Number 40. Concentration of magnesium 2+ in seawater is 0.052 molar. At what pH will 99% of the magnesium be precipitated as the hydroxide? Okay, so we've got the equation we're interested in is the precipitation of magnesium as magnesium hydroxide. So it's in equilibrium with this magnesium that's in seawater solution. Hydroxide here, like that. Okay. So the concentration of magnesium is 0.052 molar in seawater. All right. And we want to precipitate 99% of it. Right. We don't have to precipitate all of it. We just want 99%. So to multiply that times 0.99, the decimal equivalent of 99%. And that's our working concentration of magnesium, 0.052, 0.99. So I get 5.14 times 10 to the minus 2 molar magnesium. We want to precipitate all of that. So how do we precipitate all that? We do the calculation of the Q, where the Q equals the KSP. Excuse me. So the KSP is given as 8.9 times 10 to the minus 12. Oops. Got my coefficient. 8.2 times 10 to the minus 12 is the KSP. And, excuse me, thank you. There we go. And this expression is magnesium concentration, 5.14 times 10 to the minus 2. And that's our unknown. Hydroxide ion concentration squared. Okay, so we can find out what the hydroxide ion concentration has to be in order to precipitate that much. All right, so let's see. I'm going to divide this one into that one. Exponent 12, and then 5.14 exponent minus 2. And this is 1.73 times 10 minus 10 equals hydroxide ions squared. Now all I have to do is take the square root of that value. And that gives me 1.32 times 10 to the minus 5 molar. All right. What was the question? At what pH? Okay. So we can calculate POH pretty easy here, right? Just the negative log of that value. Log, change the sign. So that's 4.88. And the pH then is 14 minus 4. I get 9.1 pH.
Now, what did you do right there? You got the 1.73. And the
Here?
hydrox, yes.
Yeah.
How did you get the 1.3?
Square root.
Okay, so you done the square.
Square root of both sides. Yeah. This is the square root of that. And this is the negative log of that. And this is POH subtracted from 14. And the pH 9.12. That pH will precipitate 99% of the magnesium in seawater, as given in the problem. Okay,
He doesn't make it log, he gets it.
correct. Yep, just take the negative log of this value. That gives you this value.
So. How do you think that 5.14
Oh, times.
times?
Yeah. This is 99% of that value. All right. That's 40. And 41. Let's see, we have a solution containing 0.018 moles of iodide, 0.018 moles of bromide, 0.018 moles of chloride. When the solution is mixed with 200 milliliters of 0.24 molar silver nitrate, how much silver chloride precipitates out? Let's see. Okay. So we're starting off with, well, let's see, number 40. Notice that each one of these solids follows the same pattern of solubility. Oops, iodide, sorry. Right, for every one of these, you get one of those, one of those. It's the same for each one. So the next one is bromide. And the last one is chloride. Okay, and the KSP for each one, let's see, yeah, I click over here. KSP for each one, first one is 10 to the minus 16. Second one is 5 times 10 to the minus 13, okay? And the last one is 1.6 times 10 to the minus 10. Okay, since these follow the same pattern, then we can compare their solubilities in terms of their KSPs. Right? Because if we calculate the solubilities, we're going to get the same, it's S times S equals that, S times S equals that, S times S equals that. So since they follow the same pattern, we can say which one of these is more soluble than the other. Silver chloride is more soluble than silver bromide. And silver bromide is more soluble than silver iodide. What that means is this one is going to completely precipitate out, more than likely. If we got 0.24 molar silver nitrate, we're starting off with 0.018 mole of each one of these. 0.018 mole. 0.018 mole of each one of those ions. And if we have 0.24 molar silver nitrate, let's see. That's 0.24 molar silver. I'm just curious. Let's do this. 0.24 molar. What's the Q for that one? This is not molarity. This is 0.018 divided by 0.2 liters equals what?
Just that or the 2.4 with it.
Just this. This is a 0.24 is in molarity. This is in moles. So we got to calculate molarity. Is 9 times 10 to the minus 2 molar. So our Q is not that value. Our Q is this one times that one.
Is what one times what one?
This one times that.
Okay.
So this is 2.16 times 10 to the minus 2. Okay, we're still good. All right. So this concentration is going to be the same for each one because it's the same number of moles of each one. 0.2. So we got 9 times 10 to the minus 2 molar and 9 times 10 to the minus 2 molar chloride. This is bromide. This is chloride. And this is iodide. Okay. So we're starting off with 0.24 molar silver nitrate. Actually, let's do it by moles. Yeah, I think that'd be better. If this is 0.24 molar, how many moles of silver are in solution? Do we start with 0.24 times, right? Molarity times volume. 0.24 times 0.2 is 4.8 times 10 to the minus 2. So it's 4.8 times 10 to the minus 2 moles of silver. Right? So we're going to use up 0.018 of that, minus 0.018. And that gives us 3 times 10 to the minus 2 moles of silver left over. Then we're going to use up 0.018 of that. So what does that leave us for this precipitation?
What is that? 3.9 times 10 to the what?
Oh, sorry.
-2.
-2.
And the next one would be 1.2 times 10 to the -2.
Yeah. Moles of silver. Okay. So 1.8 times 10 to the minus 2 chloride. Right
How do we get the 1.8?
here. So we're going to use up 1.8 times 10. You know, that uses everything up. That uses it all up.
On your work problems, it says so you take the
Oh,
silver minus the
yeah.
chloride, get that, and then
That means that there's no silver left. Right? We use it all up. So how much silver chloride precipitates out? All of it. So that means we precipitated out 0.018 mole of silver. Oh, the answer's in grams. We got to convert this to grams. That's the problem. Got to read the question. It helps a whole lot. All right, what's that? Molar 107.87. 7.87. This is how much silver precipitates out. Now, did it say silver or silver chloride? Silver chloride. So it's not 107.87. It's 107.87 plus 35.45 for the chloride. This is silver. This is chloride. So it's 2, 3, 13. Yep. 143.32 times 0.018.
by that 1.2. 1.2 times 10 to the -2. Because you're doing that.
Yes.
Silver chloride.
Thank you. I would have eventually figured it out.
Hey, at least we're able to help you. He's stressing us all out over here.
Right, so that's 1.2 times 10 to the minus 2. And this is silver chloride. $1.7 grams. There.
Yes, we got it. Better open that door.
Yeah,
Cool you off a
we
little.
need a big fan. It's up to 76 in here now. I think when I post this video, I'll have to do some trimming. Save you the trouble of watching all that mess. Okay, we got another qualitative problem. When a mixture containing analytical groups 1 through 3 is treated with hydrogen sulfide, which cations are expected to precipitate? In acidic H2S, we're going to precipitate out the first two groups. Right. The first group coming out will be those that precipitate with low concentrations of sulfide. Group 2 comes out with higher concentrations of sulfide. Actually, the first group comes out with chloride. Yeah, it comes out with chloride. And then the second group comes out when we add hydrogen sulfide. So the only thing left over is 3. So 1 and 2 are the groups that we remove. We precipitate out groups 1 and 2. All right, 46. We're doing on time. 46. The cation M2 plus reacts with ammonia to form a series of complex ions as follows. All right, so we're starting off with this metal ion, and we're adding ammonia, and we're going to end up with 3 ammonias. So the overall equation is this one, right? And we have M and ammonia 3 times. Ammonia is neutral, so we still have the 2 plus charge. And this is an aqueous solution. And that's the overall. A 1 times 10 to the minus third mole sample of the metal is added to 1 liter of 15 molar ammonia. Choose the dominant species in the solution. There is a whole lot of blue smoke in this problem. To answer that question, it doesn't matter that other stuff. All you need is to look at that equation and say, what are the K values? The K1 value is 10 to the squared. So when that first ammonia attaches to the metal, its equilibrium is way to the right. And whatever that produces goes to the second equation. It goes way to the right. And then whatever that produces goes to the third equation. It goes way to the right, 10 squared. So to answer the question, the dominant species in this solution is that one right there. Okay? Because every K is to the right. I mean, if we wanted to do the K for this formation, the overall K for this formation, it'd be 2 times 3 is 6, and 6 times 2 is 12. That tells you it's way to the right. Either way works to answer that question. $47. What is the concentration of nickel 2 plus aqueous ion in 0.05 molar nickel nitrate solution that is also 1 molar ammonia? And the KF formation for the hexaamino nickel 2 is 5.5 times 10 to the 8th. Okay, what's the concentration of nickel? Okay. So if we know what the KF is, then we can say the nickel 2 plus in solution is combined with 6 ammonias. And it's in equilibrium with this complex ion. Okay. And the KF value is 5.5 times 10 to the 8th. All right. What's the concentration of nickel in a 0.05 molar nickel nitrate solution? All right. Let's say this is going to be the KF for this one is going to be the complex ion. Ammonia's first power, and then the reactants here, ammonia to the 6th power. Okay. Now, so if this is starting and this is ending, there we go. So let's say, what's 6 times this value? Because it's going to take, it's going to take that much molarity over here. So 6 times 0.045.
0.27.
0.27. Okay, that's how much we're going to use up. That means we use all this up. We use that much up. 0.27.
0.73.
Thank you. And then over here, we produce 0.045, right? 0.045. There we go. Oops. All right, that's the stoichiometry part. If we say that all of this is used up to make that, then we can set up our equilibrium. Excuse me. I believe. Better check to be sure. Yeah. Okay. Now I can set up my equilibrium. So that's the stoichiometry. Now we've got, actually, this is also equal to the initial. So what's the change that gives us the equilibrium? All right, since this is 0 now, we're going to get a shift back this way. And we're going to have a change. We're going to add some here. And for every one of these, we get 6 of those. Right? And then we're going to lose the same amount that we gain over here from this side. So this is minus X. Okay, so now at equilibrium, we have X here. We have 6X plus 0.73. And we have 0.045 minus X. Okay. Now this is going to be up here. We're going to have 0.045 minus X to the first power. Then we're going to have nickel, which is X. And we're going to have ammonia, 6X plus 0.73 to the 6th power. Now we're going to have to use some tricks. This value is huge. Right? So how much is going to come back this way? Not much. Right? That X is going to be very small. So if that X is very small, then we can save ourselves some trouble by getting rid of this X right here. Actually, we're going to get rid of both of these X's right here. That one. So now we're approximating 0.045 over X times 0.73 to the sixth power. All right. Now it's just math. So if we bring this one over here, it's going to be 0.73 to the sixth power. I get 1.5 times 10 to the minus 1. And that'll be 5.5 times 10 to the 8th here. This will be 5.5 times 10 to the 8th times one, let's see. That's close enough. I can use standard notation for this one. 0.151 X. I just took this one to the sixth power times X. That's this one right here. And then I'm going to multiply it by 5.5 times 10 to the 8th. So I get 8.3 times 10 to the 7th equals what? Oh, well, I forgot the X. X. And this is still over here on this other side, 4, 5. So X is going to be this one divided by that one. 3 divided into 0.045. Did I do that right? I better do it again. Yep. I got 5.4 times 10 to the minus 10. Now, was that the question? What's the concentration of nickel? Yeah, X is the concentration of nickel. 5.5 times 10 to the minus 10 molar. 5.4, excuse me.
You divide the 8.3.
This one, I divide that into this one because I want to keep X on this side. So I divide this both sides by 8.3 times 10 to the minus 10 to the 7. And that gives me the X, which is, by choice, the concentration of nickel at equilibrium. So my mistake was trying to do equilibrium right off the bat. I should have done stoichiometry first.
I figured it out. So look at my calculator.
Okay, let's see. How many more do I have? Okay, 50. Let's see if I can do this one without stumbling over myself. Okay. I need a new marker. That one's giving that on me. The KF for the complex ion that we're going to be working with today is 1.7 times 10 to the 7th. KSP for silver chloride, 1.6 times 10 to the minus 10. Calculate the molar solubility of silver chloride in 1 molar ammonia. This is a good problem to work with. So the molar solubility. Okay. We're going to take silver ions and combine them with ammonia. 3 of these, right? Or 2. 2. And make our complex ion. There we go. And in the same solution, we've got silver chloride. Okay. If we're going to calculate the molar solubility of silver chloride, we should be able to combine these equations. All right, let's put the K value for this one is 1.7 times 10 to the 7. And for this one is 1.6 times 10 to the minus 10. Okay, if we combine these equations, then we have silver cancels out. And we have silver chloride on this side plus 2 ammonias is in equilibrium with the complex ion plus chloride ions. This is aqueous. This is aqueous. Okay, and the K for that is those two multiplied by each other. 1.7 to the 7th times 1.6 to the minus 10. So I get 2.72 times 10 to the minus 3. All right. So if we're looking for the molar solubility, and we've got, let's see. I don't trust myself. Okay. Yeah. Now our equation becomes what? It's 2.72 times 10 to the minus 3 equals the complex ion. Oops. H. Here. Plus times the chloride ion concentration divided by sorry, NH3 squared. All right. So what is our initial concentration here? 1 molar ammonia. Okay. And molar solubility of silver chloride. Okay, that's all we're given. And we're going to say 0 here. 0 there. So what's the change? Well, it's got to go that way. So for if we say the solubility is in terms of this one, but it's not part of our expression, of course, then for every one of these, we need 2 of these. And for every one of these that solubilizes, we get 1 of these. And 1 of these. Okay. So at equilibrium, we have 1 minus 2s ammonia, and we have S of the complex ion. Yes, and then we also have S of chloride. So 2.72 times 10 to the minus 3 equals, this one is S. This one is S divided by 1.0 minus 2S squared. Okay. S times S is what?
X squared.
X squared. Yep. Okay. And we can pull that square outside. So we have S over 1.0 minus 2S. That whole thing is squared. So if we take the square roots of both sides, and what's the square root of 2.72 times 10 to the minus 3? I get 5.2 2 times 10 to the minus 2 equals S over 1.0 minus 2S. So 1.0, see, 1 times this is 5.22 times 10 to the minus 2, and minus 2 times that, S, 1.04 times 10 to the minus 1, S is equal to S. Okay, I just took this group right here, multiplied by that, that's this. And S would stay on that side. So now we're going to add this to both sides. So we can get S on the same side. So if we add 1.04 times 10 to the minus 1, S, to both sides, we get 5.22 times 10 to the minus 2 equals, I'll just do this, S plus, that's 0.104, isn't it?
Oh, no, you lost me whenever you done one.
This one?
Yeah,
Okay, I took this group and multiplied it by that.
so you just do 5.22 times 10 to the negative 2 times 1.0 minus 2.
Now, 1.0 times this is the same number.
Yeah.
And then minus 2S is 2 times this number, S. Okay. And then I took the S term and put it on that side as a positive. So this is 1.104 S equals that value, and S would be this one divided by 1.104. So I get S equals, or the molar solubility of silver chloride is 4.7, excuse me, rounded off. 4.7 times 10 to the minus 2 molar. Okay. Two more. You got time? I think we get 12, 13 minutes. $52. Excuse me. See, for this system, 500 milliliters of 0.02 molar manganese nitrate mixed with 1 liter of 1 molar sodium oxalate. Oxalate ion acts as a ligand to form a complex ion with manganese, according to this equation. Ooh, this is going to take some work. Let me see. What's the next one? Molar solubility of lead 2 chromate in. Yeah. Okay, 53 would be easier to do. Is that it? Yeah, that's the only ones we have there. Let me do 53 first, and if we have time, I'll do 52. Because 52 is going to take some mental gyrations. And 53 is fairly straightforward. Molar solubility of lead 2 chromate in sodium thiosulfate. All right, so we've got solubility. This is like our solubility of silver chloride. In this case, we have we're trying to solubilize lead 2 chromate. 2 plus chromate is also 2 minus. So that's the formula. And it's going to form this plus that in solution. And the 2 times 10 to the minus 16, the KSP, 2 times 10 to the minus 16. Okay. And then we're going to form a complex ion with it using lead 2+ ions. And then the thiosulfate, S2O3, 2 minus. And we're going to form this complex ion. Charge. Okay. And the K for this one is 2.2 times 10 to the 6th. Okay. See, I need to balance that. There we go. Okay, so if we combine these two equations, then the lead ions cancel, and we're left with the solid plus the thiosulfate ions are in equilibrium with the complex ion plus chromate. There we go. And the K for this is the KSP times the KF.
Both are pounds.
Times. So the K is not particularly large, but it's better than that. So we're going to solubilize some of it. All right. So what are the initial concentrations? We need to find out the solubility. All right, so the initial concentration is 0.055 molar thiosulfate. 0.055 molar thiosulfate. And that's all we need. Right? Initially, we start off with 0 here and 0 here. The change is going to be solubility term for this one. Right? And for every one of these, you need 3 of these. Okay. And for every one of these that you lose, you get one of these over here. Plus one of these. So we have 0.055 minus 3s at equilibrium and an s and an s. So our equilibrium expression, take a shortcut because we're running out of time. We're going to have s times s in the numerator. And in the denominator, we're going to have this term, 0.055. Actually, it's to the 3rd power. Right? Minus 3s 3rd power. Let's see. That does present a dilemma. I did these right. Did I do that right?
Why didn't we just stop when we added the case or no, cut the case together?
Oh, wait a minute. Oh, we need the molar solubility. This is the equilibrium constant. It's not the solubility.
No.
This is the solubility. I was looking to see how I simplified it. Okay. So we're going to simplify by saying that 3s is very small compared to the 0.055. So that means we have s squared over 0.055 cubed equals 4. That's 10. So I'm gonna cube this and multiply it by that. Okay, 7.32 times 10 to the minus 14 equals S squared. So S is just the square root of that value. 2.7 times 10 to the minus 7. Okay. That's the molar solubility. Let's see, what would the solubility be for just this? It'd be the square root of that value. Right, square root of 2 times 10 to the minus 16. (1.4 times 10 to the minus 8). So we've increased the solubility a little more than a magnitude, order of magnitude. It's not much, but it's better. All right. I don't think I can do the other one in
You said you had the square, you squared the 2.7.
square root. Square root of that, square root of that.
Gives you the 3.7,
Uh-huh.
and that's the answer.
Yep. Because we chose S to be the solubility.